Hello, we're looking at section 7.2 now, and if things are a little bit ragged today, part of the problem is I'm doing this from my home right now, having some technical difficulties at school, at my office, and the situation, the setup here isn't nearly as nice. I don't have as much room, and I may very well be interrupted by a cat, and who knows what else might happen. Okay, we're looking at section 7.2, which talks about chords of circles, and section 7.2 and 7.3. These two sections contain some sort of esoteric type results that you may never teach, and you may never see much use for. What is important in these sections is not to worry about memorizing results, but to understand what they say, be able to use them in practical situations, and somewhere down the road realize that you have seen these ideas and you can locate them if you need to. Some of these ideas are very useful for mechanical applications in physics and engineering, and whenever a person is studying those courses, if they haven't seen some of these, they don't know what to do with them, then that's going to put them behind. They'll be at a disadvantage. Okay, so today's section has to deal with chords and how chords are related to each other in the circle. Now, basically, a chord is just a line segment with two endpoints on a circle. So let's see, where is everything? Okay. It is a segment whose endpoints are on a circle. So here I have two chords. I have the chord A, B, and I also have the chord CD. Now CD is actually a diameter, so it is a chord that runs through the center of the circle, and it is the longest possible chord that can be formed on this circle. Got a few theorems here. Some of them are fairly easy, and some I'll skip the proof, and some of them are a little bit strange, difficult as well. Okay, 7.4. The perpendicular bisector of a chord contains the center of a circle. Okay, so here I have chord AB, and the segment that's a perpendicular bisector of AB should be go through the center of the circle. We're actually going to do it in a little bit different order than the book does here. So let's suppose, and I'm going to write this out not as a two-column proof, but as a rather prose proof here in paragraph form. So let's start with what we're going to suppose. Suppose AB is a chord with a circle with centers O. So we could just refer to this like the book does as calling this circle O, just by naming the center. Okay. Now, let's let C be the midpoint of AB. Okay. By the way, one of the problems I've assigned in this section is number 37, and I think you'll find part of the proof, or at least an idea for the proof, in what I'm doing here in section 7.4. So let's let C be the midpoint of AB. Okay. And so it'll be about here somewhere. Okay. And because C is the midpoint, this means that AC, that distance, and BC are the same. Okay. Or let me write it in terms of congruences. The segment AC is congruent to the segment BC. Okay, so these two segments are the same. I guess I can make a little mark there. All right. Now let's draw in some additional segments. Let's draw in OA, OB, and OC. Okay, and I'll use my line. Oops. I'll use my line tool here. Let's make it that way, and let's make it blue as well. So OA, oops. OA, OB, and OC. Now, OA and OB are congruent to each other. Because they are radii of the circle. Let's put little marks there. This and this are the same. Of course, OC is congruent to itself. Okay, and that's the reflexive property. So I have two triangles here, ACO and BCO, and I have paired up their sides in such a way that they're congruent. So by side, 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 triangle ACO is congruent to triangle BCO. Okay, now let's see. What does this tell us about the angles at C? Okay, these are corresponding parts here. Angle ACO must be congruent to angle BCO. Okay, now these are two adjacent angles, and their exterior sides here form a straight line. So since CA and CB form a straight line, okay, then we have 180 degrees here. ACB is a straight line, so it's 180 degrees. Then the measure of angle ACO and the measure of angle BCO have to be 90 degrees. They're equal and they have to add up to 180 degrees. Well, I think this does it, right? So CO is the perpendicular bisector. Let me change that. Back up a little bit here. I want to look at the line CO, not just the segment. It's the perpendicular bisector of AB. Okay. It was the bisector because I chose the midpoint, and all of the triangle stuff here shows that it happened to be perpendicular. So obviously, since O is a point determining this line, the center is on the perpendicular bisector. Okay, and when I'm done with the proof, I like to put a little box here saying I'm finished with it. Okay, pretty straightforward proof. Theirs is a little bit different, but it still relies on showing that you have two congruent triangles there. So I'm going to do a few more, look at some corollaries here, and I'm not going to prove these because I think they're pretty straightforward. Okay. Corollary 7.5. The intersections of the perpendicular bisectors of any two non-parallel chords is the center of the circle. Now this is, as I said, this one's pretty straightforward because the previous theorem said that if I have a chord like AB here, its perpendicular bisector must go through the center. And if I have another chord, like chord CD here, its perpendicular bisector must go through the center. So consequently, as long as these chords are not parallel, their perpendicular bisectors are going to be different, and the center is going to be on each one of them. And two different lines, when they intersect in exactly one. If they intersect in exactly one point, that one point in this case has to be the circle. So what this does then is this gives us a really easy way, perhaps, to do the following. This is an arc of some circle. This is number 24, page 379. Somewhere down here is the center. And what we want to do is to use a compass and straight edge to find the center of the circle where this arc belongs. Now, if you're doing any of these problems from the book where they have a figure that you're supposed to work with, trace that figure. Put a piece of paper over top of it and trace it. Don't just kind of go off to the side and draw something that you think looks like it. Some of these figures are drawn in a specific way, and unless you have them traced accurately, you won't get the right result. Now, unfortunately, I can't really use the compass and straight edge very easily on this. I'm going to try, but the last time I tried to use the compass portion of this smart notebook program, it was kind of a disaster. So, but if I can, I will. Okay, so here I've got this arc. Now what I need is some chord on this arc. Doesn't matter, any old chord. So I'm going to draw, I'm going to draw one like this. Okay, now let me mess with it a little bit to make it a real chord. Okay, so there's a chord AB. Now what we want to do is to construct the perpendicular bisector of this chord, because the previous theorem said that when you have the perpendicular bisector of a chord, it goes through the origin. So to construct a perpendicular bisector, let's see if I can do it. I've got to get my goofy compass out of here. I practiced this earlier and it actually worked a little bit. Okay, so you'll be able to do this a lot better on your own than I will. But what we need to do, what I need to do is to construct a perpendicular bisector of this thing. Put this on here. Okay, so set your compass so that I didn't quite get it here. I'm going to see if I can move this guy a little bit to where it actually is. And the perpendicular bisector will be the line that goes through these two places. Now give me a second to, yeah. That's pretty much perpendicular bisector of that chord. Now, take another chord, any old chord. Just not the same one you had, and it doesn't matter how long it is or anything, and it doesn't have to have any relationship to this previous chord. I'm going to draw it here, and it'll take a little bit to make it a real chord. Construct the perpendicular bisector of that. Now I'm just going to eyeball this because this compass is kind of goofy. The perpendicular table, let's make this a different color too. Okay, great. The perpendicular bisector here should supposed to be green as well. And let's see, that doesn't quite look perpendicular to me. That looks more like it. And I think I may have to shift it a little bit to the left to make it. That looks kind of like a perpendicular bisector to me. Okay. This theorem says that the intersections of perpendicular bisectors of any two non-parallel chords is the center of the circle. So this must be the center of the circle right here. So let's see. Let's draw a circle having that as the center and see if it matches this arc. So here's my circle tool. We'll start here, and yeah, that does a pretty good job, doesn't it? Okay, so if you have an arc, a portion of a circle, or a whole circle, all you need to do is to draw a couple of non-parallel chords, find their perpendicular bisectors, and that will give you the center of the circle. Okay. And actually what you can do with this, if you have any three points that are not collinear, 1, 2, 3, draw the perpendicular bisector of each segment, you'll have a center, and you can find the circle that includes those 3 points. Now that points to one of the real reasons I'm doing spending time on sections 7.2 and 7.3 is I really like section 7.4 where we do constructions with circles. So if I thought we could skip some of this material or more of this material, I might do that. But I don't think so. I think you really need to do this in order to get to section 7.4. Okay, we've got a few more theorems here, or little corollaries. These are just really quick results. Corollary 7.6. If two circles, O and O prime, intersect in 2 points A and B, then the line containing O and O prime is the perpendicular bisector of AB. This is pretty straightforward in that these 2 points A and B, when you have two circles intersecting here, the 2 points A and B, they form a chord for a circle O. So the perpendicular bisector of AB goes through O. Okay. They form a chord also for circle O prime. Okay. So the perpendicular, let me see what I am here. The perpendicular bisector of AB must go through this point, and the perpendicular bisector of AB must go through this point. Of course, perpendicular bisectors are the same, then that means the line through those 2 points is the perpendicular bisector. So that's just using the theorem 7.4 twice. Okay. Because this chord is a chord of both circles, the perpendicular bisector goes through both centers. Okay, so not a whole lot to do on that one. Let me write something down here. So the looks funny, doesn't it? O prime. The perpendicular bisector of AB must contain O because AB is the chord of circle O. Okay, and the perpendicular bisector must contain O prime because AB is a chord there of O prime. So that means the OO prime is the perpendicular bisector of AB. Okay, and that's the proof of that thing. Let's see what else we got here. Theorem 7.7. Now we have a real theorem here. This is one of these theorems that, well, again, this is not anything we're going to, that you'll probably run across unless you do some rather specialized work with circles in some sort of engineering or physics application. And in that case, you really do need to know these things. Otherwise, you'll have to learn them. And you just slow yourself down. So theorem 7.7. Okay. If two chords intersect, the sum of the measure of any one of the vertical angles formed is equal to half the sum of the measures of the two arcs intersected by the vertical angles. Okay. So what we're going to do here is I have circle, and I don't even care where the center is. It's here somewhere, but it's not an important point in terms of this this theorem here. So A, B, and CD are chords, and they intersect at E. And I'm going to look at AEC. I'm going to look at this particular vertical angle. Okay. So we're talking about any one of the vertical angles. Well, I've just picked one here. I want to show that the measure of AEC is 1/2 the measure of this arc plus the measure of that arc, which would work the same for angle DEB. Okay. Now, if I was looking at the angle AED, I'll be looking at the two arcs from AD and CB. Okay, now on this one we're going to be looking at angles and arcs, so we have several theorems from a previous section here. So on 7.7 here, let's construct one line segment. So for the proof here, okay, let's start by constructing. In other words, since this line segment wasn't given, we'll need to construct it or draw it in here. Let's look at CB. So let's draw that in down here. Okay. Now, when looking at CB now, I have a couple of inscribed angles. Okay. So we'll go back here. Let's construct CB. Okay. Now, looking at CB, I have a couple of inscribed angles here. Okay. I have then angle CBA. So I have this angle. Okay. And what it does is it inscribes arcs AC. Okay, this arc over here that I've got the one notch in. And if you go back to your inscribed angle theorem, so the measure of angle CBA is 1/2 the measure of the arc AC, and this is your inscribed angle theorem. And I forget the number of that one. Okay. Now, let's look at a different angle. Angle BCD. That's this angle here. Okay. It inscribes arc DB. So by the same reason, inscribed angle theorem, the measure of angle BCD is equal to 1/2 the measure of arc DB. Now, what do we have here? I look at these two angles down here. Well, they're part of a triangle. And the vertical angle I'm interested in, this angle E, is actually exterior to that triangle. So angle AEC is exterior to the triangle EBC. Okay. So by the exterior angle theorem, says that the measure of angle AEC is equal to the sum of the measure of its two remote interior angles. So that's going to be the measure of angle ECB plus the measure of angle EBC. Okay, so this angle is the sum of those two. Well, I've already got those two angles here. What ECB is the same thing as, where am I here? BCD. This is the same as the angle BCD. Okay, ECB is the same as that. EBC is the same as CBA. So this is 1/2 the measure of arc DB plus 1/2 the measure of arc AC. So if you factor out a 1/2 and then add the two arcs together, you have the measure of AC. Oh, let me write them in the same order I had. The measure of DB plus the measure of AC. And the only difference I've got here is I've got things in a little bit different order. Also, if you look in the book, you notice I'm being a lot more careful using the symbols for measure, because we're not really adding arcs together. We're adding together the lengths of the arcs. Okay, so let's put a box around it because this rascal's done. Let's see what I've got next. Let's do an example. This is from page 379, I believe. Okay. I have a circle here with some chords drawn, and this is actually there's 6 different problems that go along with this, so I may not use all the chords here. But in number 3, we have arc AD is 125 degrees. So this arc down here is 125 degrees. And arc BC is 173 degrees. Okay. And we're asked to find a measure of this angle. Okay, BEC. Okay, so let's go back to the theorem. It says that the measure of any one of the vertical angles is equal to half the sum of the measures of the two arcs intercepted by the two vertical angles. Okay, so chord AD doesn't have anything to do with this problem. So here's a vertical angle here, BEC. Here's its neighbor. Okay, and the two arcs we're talking about, and I can't draw it on this, is this arc. Let me try that again. Yes, this arc, and those are the two arcs we're talking about. Okay, so the previous theorem says the measure of angle BEC is 1/2 the measure of the arc BC. I guess I've got this in parentheses, plus the measure of the arc AD, the arc that's formed by its companion vertical angle. BC arc is 173 degrees. The AD arc is 125 degrees. This is 1/2 of, let's see, 298. And half of 298 is 149 degrees. Okay. So that one's straightforward. Number 4 is a little bit tougher. Yep. Okay. So let's do this in a different color so that we'll know, because I'm not going to mess up what I've already worked with. Okay, we're looking at angle AEB in this case. So this would be its companion vertical angle, CED. So let's write down what we know about angle AEB. Using the previous theorem, the measure of angle AEB is 1/2 the measure of the two arcs, this arc and this arc. 1/2 the measure of AB plus the measure of the arc that's sort of vertical arcs. I don't know if that's such a thing, but the arc that's vertical to it, CD. Plug in the numbers we know. So 35 degrees is 1/2 of AB, 24 degrees, plus, well, I don't know what the measure of CD is. Okay. So this is a simple little algebra 1 thing here. I'm going to multiply both sides by 2 to cancel off this fraction because I don't like fractions. 2 times 35, 70 degrees. The 2 and the 1/2 cancel. So that's 24 plus a measure of CD. So 70 minus 24, which is 46 degrees is the measure of arc CD. Okay. So write down the equation, plug in what you know, and then just do a little bit of linear algebra type arithmetic. Now, Theorem 7-8 is, again, one of these theorems that you're never probably going to have to use. However, I must admit that several years ago I was doing workshops for students studying for Praxis 2 exams, and a problem involving this showed up on there. So they pop up every now and then. You're supposed to know them. You don't have, of course, when you take the Praxis 2, you're not expected to know everything, but I have seen one of these chord problems on Praxis 2 study guides. Okay. So Theorem 7-8, if two chords of a circle intersect, which I've got here, AB and CD intersect at E, then the product of the lengths of the two segments formed on one chord is equal to the product of the length of the two segments formed on the other chord. Okay, so AE times EB equals CE times DE. Okay, so this is actually a similar triangle type problem. So let's start by making us some triangles here. Okay. Let's start my proof. But I don't want to do red. Let's pick a different color here. Let's work in green for a little while. Okay. So let's draw or construct, however you want to say it. Let's construct the segments CB and AD. Okay. So here's CB and here's AD. Okay, let's make these guys. We're going to do green on this one. This looks like a green theorem to me. Okay. Now, let's take a look here. We're looking at the arc DB now. This arc. Okay. And notice that there are two angles that inscribe that arc. So let's note that angle DAB is supposed to be a B, and angle BCD both inscribe arc DB. Okay. So, okay. The measure of angle DAB, excuse me, I don't want measures. So angle DAB is congruent to angle DCB. And if you go back into the previous section, this is a corollary 7.2. Okay, so this, we have that this angle and this angle are the same. Now, do you see any other congruent angles? Well, yeah, there are several more here. Let's take a look at some vertical angles we have here. That angle AED must be congruent to angle CEB because they are vertical angles. Okay, so now, so these two angles are the same here. So now I have two different triangles here by the AA similarity theorem. And the number is not on my tongue right now. I don't know what number that is, but I have two triangles here, and I know that that two corresponding angles are congruent, so it forces the third one to be as well, which forces the triangle to be similar. So by the AA similarity theorem, I know the triangle AED is similar to triangle CEB. Okay. Once we have similar triangles, we have lots of numbers that are lots of ratios that are the same. Okay. Okay. Hence, we have this proportion that AE is to CE as, okay, these two sides correspond as what DE is to BE. Okay. And now we just have one more step. If we multiply through by, or, you know, I'm not going to use the term cross multiply because I hate it, but if we multiply both sides by CE and BE, okay, just multiplying both sides by the same number, some things cancel, and we get then that on the left side, the CE's cancel, we have BE times AE. And on the right side, the BE's cancel, and I have DE times CE. Okay. And except for the order of the factors being off over here, which you can certainly switch by commutative property, we are done. So let's do an example then. have a couple of examples to remember them. Yes, here, let's see. Problems 11 through 14 refer to this figure. I have several chords and several other things being, I have 4 different chords here. Okay. So on number 12, AE is 9.8, CE is 5.7, DE is 3.8, BE is what we're after here. Okay, so on number 12, okay, what do we know? We know that AE times CE equals BE times DE. Okay, because I'm looking at chord AC and chord BD, and when they intersect, the product of the parts of one chord equal the product of the parts of the other. Okay, so plug in what we know here. We know 9.8. We know 5.7. Over here, I don't know BE, but I do know 3.8. So if I take 9.8 multiplied by 5.7 and divide that by 3.8, I should get BE. And I believe that is 14.7. Now, just a word of caution here, the book draws pictures, but they're not drawn to scale. So if you go back through and draw an actual circle where the chords have these measurements, it's not really going to look like this thing here. Okay, now I have to pardon for a second because the cat just jumped up here on the desk. Okay, so I've got the cat off the desk now. So BE is 14.7, and oh yeah, I should put down 14.7 meters. This is a big circle. Okay, let's take a look at number 13. Okay. Number 13, BE to EC and so on. All right, so we write the same sort of relationship down here. BE times ED or DE is the same thing as AE times CE. Okay. Or EC. It really doesn't matter. So let's plug in what we know. BE is 2 EC. ED is 3.5. AE is, I don't know what AE is, but I do know if AC is 12, if from here to here is 12, then AE is 12 minus EC, and EC is just EC. Okay, so we're going to have a little bit of a quadratic thing to solve here. I've got all my numbers in. So 2 EC times 3.5, this is 7 EC here. When I multiply this out on the right side, I have 12 EC minus EC squared. Okay. Get everything over on the left side so that the square term is positive, so EC squared. And then I had a 7, but I subtracted 12. Minus 5 EC equals 0. So you factor this. And you either get that EC equals 0, which isn't going to happen, or EC equals 5. So that's your answer here. And again, don't look at the figure, although this one is probably not as non-proportional as number 12 is. Okay, so those aren't too bad. 19 is a little bit challenging problem here. It's the same sort of, we're using the same sort of result because we're talking about segments that are formed when several chords intersect. All right. But the first thing that makes 19 a little more interesting is what's going on here with, they specifically give us a diameter here. I mean, in this one, in the one on the left, we didn't have the center of the circle, and the one on the right, we do. So the first thing is to note okay, you can't read that. Let me see if I can write that a little better. So first, notice that triangle ADC is the right triangle. This goes, okay, this is a right triangle. We get back to corollary is it 7.3? Yes. This is by corollary. If you have a triangle inscribed in a circle where one side is a diameter, then the inscribed angle there must be a 90-degree angle there at D. Okay, so since that's a right triangle, we have that you can use Pythagorean theorem. AD squared plus CD squared must be AC squared. So plug in what we know. AD is 15. CD is 8. 15 squared plus 8 squared is 289. So AC, the square root of 289, which is 17. Okay, so hold on to that number. So the distance from A to C is 17. Now, what we're trying to find is AE. We're trying to find this distance. So I'm actually going to, well, let's write down a few things here. We know now we're looking at two intersecting chords. We're just looking at AC and BD intersecting. We don't need to look at anything else right now. So we know from this theorem we're working on that AE times EC or CE or EC, whatever, is equal to BE times DE. Let's see, I can plug in some of these numbers. I know BE and DE. I don't know anything about AE and CE, so what I'm going to do is I'm going to call, just to make this stuff look a little nicer, I'm going to call this amount X. Then CE is not going to fit in very well. It's going to be 17 minus X. Okay, so AE is X times 17 minus X equals BE 10 times DE times 6. Times 6. So 17x minus x squared equals 60. So bring everything over to the right. makes it a positive x squared, minus 17x, and a plus 60. Okay, now this factors as x minus 12 and x minus 5. Okay, so x minus 12 equals 0, or x minus 5 equals 0. We get x equals 12, or x equals 5. Well, which one is it? Well, if section AE goes beyond the center, okay, so AE goes beyond the center, then it has to be the larger of the two numbers. So the only reason this, so according to the picture, okay, then that's the answer. If you didn't know that it went beyond the center of the circle, if you just knew that it was on a diameter, you couldn't tell which one it had to be. Okay, so I'm just about done with this. I think I have one more thing to do here. First, I want to make a remark about number 25. This is one of the problems that is assigned. Put a piece of paper over top of this and trace it. Okay. Where this particular quadrilateral can, okay, you can get a circle through these, but if you just draw some quadrilateral that kind of looks like this on your paper, you may not be able to do that. As a matter of fact, it's likely that you won't be able to do that. Okay, and I think, let's see, now I've got problem number 36 here. I decided I want to do a proof, so make sure you trace this. This is kind of a tough proof here. Part of this is tough and part of it's kind of easy. Number 36, you want to prove that we can inscribe a quadrilateral in a circle if and only if the quadrilateral's opposite edges, opposite angles are supplementary. So this is a two-part proof. Okay, it's an if and only if, so it goes both directions. One direction is we want to prove that if a quadrilateral is inscribed in a circle, then its opposite angles are supplementary. Okay, that's the easy part. And the other part is we want to prove that if a quadrilateral's opposite angles are supplementary, then it can be inscribed in a circle. Okay, so I'm going to prove these, and I may leave out a step or two, but I think I'll put in all of the important things here. So here I've got, in part one, I've got an inscribed quadrilateral, and I want to prove that the angles are supplementary. Okay, I'm only going to prove A and C. I want to prove that this angle and this angle are supplementary. The proof is the same as what it would take to prove that the angle at D and B and the angles at D and B are supplementary. And this is real easy. Okay. Okay. And what's really easy about this is angle A inscribes arc, okay, B, C, B. So the measure of angle A is 1/2 the measure of that arc. Okay. Now let's look at this angle over here at C. Angle C inscribes arc. Okay, well, C goes from B to D, from B all the way around to D. So it inscribes arc BAD. It's supposed to be an arc. Let me write that down again. So the measure of angle C is 1/2 the measure of arc BAD. Okay, so let's write these down here. The measure of angle A plus the measure of angle C is 1/2 the measure of arc DCB plus 1/2 the measure of arc BAD. It's 1/2 the sum of these two arcs here, the measure of DCB plus the measure of the arc BAD. Well, what do we got here? DCB goes from here to here. BAD goes the rest of the way. So this is those two things add up to 360 degrees. So the measure of angle A plus the measure of angle C is half of that. 180 degrees. Angle A, angle C are supplementary. Okay. So that's the easy one. Very straightforward here. Have to be supplementary. Matter of fact, this looks like something that might have been done in the previous section. Now, part 2. This is a little bit tougher. Prove that if a quadrilateral's opposite angles are supplementary, then it can be inscribed in a circle. Okay. I'm going to do an indirect proof on this. I'm going to prove this by contradiction. Okay, now the indirect proof is, let's go here. The proof here will not show that this is true, but the proof will show that it's impossible for this to be false. Okay. That's what proof for contradictions are. And I want to pause on it. I don't think I've said this before, but when you prove something indirectly, when you do a proof by contradiction, that said you're not actually proving that something happens, you're proving that it can't not happen. Although I've made my peace with it, there are a lot of people that don't really believe in, or they don't like to use proof by contradictions. Okay. They say that all you've shown, that you never have shown for this to be true, you've just shown that it can't be false. Okay, and they like more constructive sort of proofs. So, as a matter of fact, there's a whole version of calculus and a lot of other mathematics that's constructivist in this very sense that they do not allow proofs by contradiction. And it's really a very interesting way of looking at things. I don't have a problem with it, but some people do. And it's interesting. There are debates in mathematics as to what you are and are not allowed to do. Okay. So let me kind of do this. I probably won't do this real perfectly, but so let's start by saying this. So here's my proof. Okay. Let's first, we know that there is some circle, let's just say circle. There is one circle containing points A, B, and C. Okay. And the way you find that is, well, you treat A, B, and BC like there were chords on a circle, and you find the intersection of the perpendicular bisector here, the perpendicular bisector there, and that gives you a center, and you just draw the circle that goes that way. Okay. Okay. So I'm going to scoot this circle over there in a minute. So let us suppose that let me get the circle out of the way. I'll come back to this guy in a minute. I'll get him out of the way. Get out of the way. Let us suppose that We have a quadrilateral. Where the opposite angles are supplementary. But it's not inscribed in a circle. Okay, and what I should have done is put this sentence here. Okay, so in other words, I can find a circle that goes through points A, B, and C, but this circle doesn't go through D. So there is a circle. For A, B, and C, but not D. Okay, now, so it looks something like this. I've drawn a situation where D is exterior to the circle. Okay, actually D could be inside the circle as well, but this will do everything. So this will be a good enough proof here. I'll come back and say something in a minute. So let's let D prime be the intersection of CD with a circle. So that's this guy right here. All right. Okay, so and we notice that so A, B, C, D prime is an inscribed quadrilateral. All right, let me draw that other section in there, and I'm going to need a different color. This guy is an inscribed quadrilateral, A, B, C, D prime. Okay. And what we've already shown is that we have shown that opposite angles are supplementary in part 1. Okay. So we have shown then that so hence angle C and angle BAD prime are supplementary. Okay. So this angle and this angle are opposite in the ABCD prime, which is inscribed, so they have to be supplementary. Okay, but now wait a minute. But we already had that angle C and angle A were supplementary. Okay, because we assumed we had a quad where the angles were supplementary, where the opposite angles are supplementary. Okay, so this means that angle A, which was the original angle BAD, and angle BAD AD prime must be the same. Okay, so what that means is that this point D can't be outside the circle. It must be on the circle. So I have a contradiction. I cannot have, in other words, I cannot have a quadrilateral with opposite supplementary angles that's not in a circle. So let me just make sure I say that last thing here. Okay. So this means we cannot have quadrilateral with opposite angles supplementary okay and a point and one vertex not on a circle containing the other three. Okay. Now, I don't want you to get too concerned. I've assigned number 37, and it isn't anything nearly as hard as this. 37 is a pretty straightforward sort of problem, especially if you look back and see what I did on one of my earlier proofs. Okay, so I think this will get you through the homework if you haven't already worked on them, and good luck. Let me know if you have trouble.